let's move to another presentation, and I'm really pleased to welcome Professor Dr. Volker Lohweg. Volker has been the Institute Director of the Institute of Industrial IT at the Ostwestfalen-Lippe University of Applied Science since 2017. He represents the Discrete Systems Group with the groups image processing and also pattern recognition, as well as sensor and information fusion in research and teaching. Volker's research interests are in the area of technical cognitive systems, with a focus on industrial real-time image processing and pattern recognition. Well, Volker, thank you very much for joining us today with a presentation which is about one of the topics I think that is of huge interest in the industry, which is actually less data, more. Sparse data and artificial intelligence and machine learning, a look at the industrial world. This is the title of your presentation. Thank you very much for joining us today, and the stage is yours.
Thank you very much.
Screen.
Yeah, thank you very much. Yes, let me check. Hopefully you can see my presentation slides now.
Perfect.
So dear all, let's come to the second talk for this afternoon, is less more. Sparse data in artificial intelligence and machine learning, a look at the industrial world. Well, Lydia started just nicely in the direction where we have to use a lot of data. So, and in many cases, we have large amount of data, up to big data, and this is available in the today's world, so we can have a positive check mark here. Wonderful. And data, of course, is collected everywhere. We are going towards a digital society, as we all know. So here we might also do a check mark here. And third, also companies, of course, collect in many cases enough data in systems and equipment during production. So here we can also do a check mark in general. And furthermore, many approaches in production, for example, predictive or preventive maintenance and designing individual products, so Industry 4.0, for example, but also robotics, mobility, business modeling are, of course, largely based on artificial intelligence. And of course, in many cases, when we talk about machine intelligence, are based on machine learning methods. So this is all in general wonderful on one hand, and we are all loving data. But what is if we do not have enough data? And this is under practical considerations in not all, but many cases the case, so to say, if you like, especially in industrial applications, production applications, we faced many times the situation that data is not always available in sufficient quantities. So we do not have enough data. This is also one general comment. I will come to this later on. And even if we have enough recorded data, if you like, in many cases, the data recorded is repetitive. So it's containing more or less the same information with some, let's say, different structures here in this context. However, in many cases, we found that we have only few data sources and sometimes also few data points. And this is usually summarized in science, but also in practical considerations in the term sparse or even scarce data, or if you like data sparsity or data scarcity. So what is this? If we take a look into a dictionary, sparse adjective, what does it mean? Only present in small amount of numbers and often spread around over a large area. So this does sparse mean, and on the other hand, scarce also adjective. If something is scarce, then it is not enough, and this is more or less the interesting part, and it's only available in small quantities. And this is what we sometimes fail under real world or real life situations, for example, in production machines. And this creates, of course, uncertainty in data. And this is what I would like to talk about a little bit more. So with this, we come to two definitions, which, by the way, you can also read in the papers and books which are highlighted here below. The first is the so-called aleatoric uncertainty. Quite interesting word, comes from Latin. Aleatoric uncertainty refers to the inherent variation of an object, of a concept, process, or of a phenomenon, and it's random and non-deterministic in its nature. We could also call this artifacts, or if you coming from, let's say, the electrical world, then we would call it noise or something like that. And we can work on that by filtering and to reduce the uncertainty. The more interesting part is a little different. This is called the epistemic uncertainty, coming from Latin, from the Greek, sorry, and it does mean there is not enough knowledge. So we are talking about epistemic uncertainty, and which results from a lack of knowledge about whatever you like, a concept, a process, an object, and so on. And this lack causes by incomplete, not available, or even inconsistent information. And this is the interesting part where we also do our research in this context. And if you take a deeper look in this, in the imperfection of information or even knowledge, then we have imprecise, incomplete, or even inconsistent information or knowledge. And in the area of incomplete information, we are living in the world of sparse or even scarce information. And we are also living in the world of, if you like, context, in the case of there is no context or only a little context. And I would like to highlight one additional aspect in the context of inconsistency, and this is conflicting or conflicts of data. And conflicts of data we have in many practical applications. Let's go a little further. For example, if you take a large machine like this one here, this is a kind of a special printing machine. You see the little personnel there, and here you see also the size of the machine. And such kind of machines, and of course also other machines, also in the process industries, are equipped with many hundreds up to thousands of sensory units and also drives, etc., etc. And the inconsistency of data here, and also conflicting of data based on not properly mounted sensors, sensors which are working not quite well, etc., or which are not well maintained, is the standard case. It's not the exception in such kind of machinery, for example. So, and now where is the real challenge? Sparse and scarce data comes from due to the fact that we have in many cases incompleteness of data, and in many cases, furthermore, it's conscious. We know that we have not enough data in many cases. Furthermore, also conscious partial data labeling. In the simplest case, what is good, what is bad, for example, in anomaly detection and so on. Also conscious missing data. We know that there are, let's say, data sources which are not delivering quite well in the context. And number 4, the conscious disrespect or fate of data conflicts. And of course, other things like parameter changes and so on and so on. The interesting part is that this is in many cases the standard due to limitations in complexity in real world situations. So we are not able to describe or to model a complex system in a, if you like, perfect way. However, we as humans, we do partly at least compensate by our, if you like, cleverness or our behavior, all these, at least here 4 points where we consciously live in this world of imprecision and uncertainty and maybe conflicting data. And I would do a little, very small intermezzo here. There's a quite nice paradoxon, the Polanyi paradoxon, which is quite simply called, we know more than we can tell, because we as humans, we are quite good in detection of something is different, if you like. If you take, without any comment now here, if you take a look to this picture here, this clarifies the situation, or even if you like, this picture here clarifies the situation. And honestly speaking, my personal highlight looks like this here. And there, as humans, we are quite good, and therefore we are compensating this. And machine learning and also machine intelligence, or in general AI, has to compensate this also at least a little bit. And there is one more topic here, and this is context in data, sometimes also, let's say, mapped on contextual AI. If you take a look to a picture here, you directly analyze scene, what is happening there. And for example, for image processing and AI and image processing, this is quite difficult. Also like this, you exactly know what might be on the dog's leash here in this picture, even if you do not see this. And this we have to bring into context, if you like. So what can we do? There are several possibilities how to handle all the effects of imprecision of data. For example, what is quite also today quite traditional now is transfer learning, where we try to learn deep networks in the context, but we use at the end not the whole training for all different applications. We do, let's say, the training and the prediction and access of the network at the end of a deep learning, and the rest we leave unchanged. So we use, let's say, partly trained information from another domain and transfer it, therefore transfer learning, to another domain. And of course, yes, the purpose of transfer learning is to be able to handle scarce and sparse data. This is one possibility. Another possibility is data augmentation. So we have just only a small amount of data, and we try to change this data artificially, like this number 6 here, and we try to retrain a network. This is another possibility here in the context. And there is a third quite interesting one where I will focus a little bit more on the next slide. This is called informed machine learning. So where we put not only the data in our machine learning AI pipeline, but also prior knowledge coming, let's say, also from data, but also from experts, to, let's say, give more information to a scarce or sparse data set. And what we do, we are using, it's called information fusion, in the context of epistemic uncertainty. And this is quite intensively addressed in this research field in the last years. And we aim here in information fusion methods to extract and condense high quality information from a set of low quality data sources. So this is the basic idea. And we are using information fusion to fill in data gaps, to reduce conflicts in data, but which is possible, at least in parts, to bring in more robustness and reliability in the data, and to bring also in experts' knowledge. And what we are also try to do to perform soft sensing, that does mean we design, let's say, a sensor which is not physically there, but we design the sensor coming from different kind of data, and it's mainly used in the context of sensor and information fusion in machine and plant engineering. Where we are using different kind of sensors, as you see here in the picture, and we marriage, if you like, we fuse, of course, this in a sensor and information fusion system, and we put in experts' knowledge, and also we create action, let's say, a feedback channel into maybe a production machine, and machine learning in itself takes place in the sensor and information fusion system. We are using something which is called multi-layer attribute-based conflict reduced observation system. And this has different layers, as you can see. So we have our signal sources for the measuring of physical, but also biological or chemical, etc. effects. Then we are having a signal conditioning. This is purely, let's say, based on the sensors. And then comes, if you like, the interesting parts. We are designing so-called by some mathematics based on possibility theory and also on fuzzy set theory. We are designing attributes coming from a machine, and the attributes, you can interpret the attributes as complex features, if you like, together with importance measured by context. We generate then a global and important fusion and give out, let's say, a data result, for example, in preventive maintenance, and the machine intelligence takes place here in these boxes. And what we are also doing here, we are able with the models, what we are using to reduce conflicts if we have data conflicts. What we are doing in our, let's say, special way, we have designed a cognitive information processor, which can also be used in edge computing systems, which includes a sensor system, an interference system, our information fusion system, and a database for background knowledge, and also external semantical knowledge and experts know-how beside the information sources are put in the system. And of course, we have an action system here in the context where we do, as you have seen before, the feedback loop, and this we call cognitive information processor. So some examples, we have applied this, for example, here for a special kind of a printing machine, which prints very special, let's say, a very special process in Vulgo, if you like, for money printing, banknotes. Yes, we have banknotes, and the amount of banknotes is increasing by 6% worldwide every year, interesting enough, in a digital world. And here we are doing measuring of the whole color deck and also special other things, and where we have around 10 to 15 sensory units, and we create, let's say, around 10 features, which is not much because you get not much, and we are doing here information fusion to reduce the effect of scarce data. Another example where we did this is based on filling machines and bottles, where we designed together with the partners here on the left side an edge computing system for fast filling, sensor-based subsystem together here with Krone Innovation and KHS GmbH. And concrete what we did a learning system, a fusion system for filling these kind of bottles. And what I personally have learned that it's very tricky to fill bottles with beer because of all these effects we have. And even if you fill something which you see on the right side with water, then you see the effect, what is happening. Even if you use water, you see a lot of bubbles, etc., etc. And if you do this with beer, it's even more tricky. And by using information fusion and let this run in the in the whole machine process, it looks like this here, for example, also with water, but you see the difference. Of course, it's much smoother. And the last example I have here is a new project. It's OWL project, Artificial Intelligence for Sparse Data, where we work together with GEA, Miele, and biotech, different companies, and the two research universities of applied sciences is the Fachhochschule Bielefeld and we here at the Technische Hochschule OWL, where we combine information fusion, you see it here in the middle, with the interpretational part of artificial intelligence. And last but not least, this is my take-home message here. So data sparsity and scarcity is a real-world topic due to the complexity about application, process, and product. Epistemic uncertainty is a key phenomenon in many industrial applications, and of course, adapted forms of AI, machine intelligence, and machine learning can be used for sparse and scarce data. And concepts and solutions are available. This is a good part. Transfer learning, data augmentation, for example, informed ML, and of course, information fusion in the context of AI. Thank you very much.